linear line intersecting at P divided by 6. Okay? Moving on. This is our sum of forces in the y direction equals 0. I already illustrated that before. Okay, now we have to do the moments. So the sum of moments in the end equals 0. And now we're starting the sum of moments from here. Everything, all the forces towards the left. Okay? So we start off as M because it's the force M demonstrated here. M. Don't forget. Multiplied by P on L. Now here's a tricky part. Now, oh sorry, not multiplied by, it's going to be plus P on L multiplied by X multiplied by X on 2 because the distance to the midpoint is X on 2. Alright? Subtracts the entire distance of the B multiplied by RA, as you can tell by the diagram. Here. Entire distance. The whole thing equals 0. Sorry about that. Just quick mental math. 6.17. Alright, so it's in the end you'll get M equals 7px. L subtracts 3px squared divided by 6L. Now this is a squared x term. Now this is an x squared term. Now because it's an x squared, it's going to be a line, but it's going to be curving. Okay, it's a contour line, if you may. Now we have to actually find the intersecting point from the start to the end, but we need to know how that contour line will actually go about. What kind of curve will it create? Okay, so let's start off with the basics. Now the intersecting point or the end point for this is x equals L, but it's a weird L. Where does this intersect? Let's see. So M equals, substituting L. Sorry, I'm just going to skip the maths here. 6pl on 3. Okay, that's its intersecting point, right? Let's just say here. So it's 2pl on 3. Okay. But what kind of curve would it create to get from here to here? Now let's work it out, shall we? Firstly, the trick about an x squared function is to find out if it's going to where's the max, where's the min, where's the max. So to find that, it's the derivative dm dx equals 7pl divided by 6l subtracts 6px divided by 6l. Okay. Make this equals 0 and work for x. What is x equal to? Alright? Just as I said, sorry about this guys, but I'm going to just skip the math. 7 over 6l. So at x equals 7 on 6l is our max or midpoint. Alright? It's obvious in our situation it's a max, but to test to see if it actually is a max, you have to use the double derivative rule. So it's d squared m over dx squared. It might be dm squared over d squared x. I'm not sure. Sorry, guys. So this term is 0 and subtracts. So you know it's a negative. There's a negative right there. Subtracts p on L. Because it's a negative term, that tells us it's a max. Alright, so our max point is here, so it's going to create a curve like that. Okay? So it's sort of max. Alright, there's a max point. Sorry for the messy hand, right? This is paint I'm using after all. Let's just create dotted lines. There we go. To a max point. That's a max point right there. Okay? And the line that we're drawing sort of awkwardly curves towards this max point here, alright? It's a really bad illustration of it, sorry guys, but you're just going to have to imagine it, alright? If you draw it to scale, well done on your part. It actually really help if you do draw it to scale. So let's moving on. Okay, so let's just smash another piece from that beam. Let's create limits between 0 less than or equal to x less than 2l. Alright, so please watch my previous videos as to why I did that, the limit. Just split a beam like that. Okay, so I'm sure you guys are all familiar with this diagram here, but there's something missing. Okay, so what's this distance here? Watch my previous videos as to what that actual how we actually work out that distance. Overall distance of the beam is x. Let me just quickly tell you though, right now, what that distance is. It'll be the overall distance of the beam, x, subtracts the minor distance to the starting point of whatever you're trying to work out, whatever distance you're trying to work out. So it's x subtracts l. Okay. So quickly moving on, sum of forces in the y direction equals 0. Okay, so therefore that's telling us that negative v plus ra subtracts p on l multiplied by the l distance to get rid of the newtons per meter. Remember I told you guys about that before. Equals 0. Moving on, we get v equals ra 7p on 6 subtracts p, and we get v equals p on 6. Okay. Now that's a positive p on 6, so that's telling us that this diagram would continue to p on 6, because it's obvious. If you look at a diagram, there are no forces acting in this part. There's absolutely no forces there, so this is going to go to p on 6, alright? What about the moments, however? There's always moments along, so let's just quickly do this. Sum of moments equals 0. Starting off, remember guys, just look at the previous parts of this video and to find out what we're doing. So m, if you don't understand that is, so positive m plus p on l multiplied by the distance of l multiplied by, to get to the point load of the distributed load, it's an L on 2 here, but what about this part? Yeah, obviously it's redundant. You've got to add half that distance plus the x minus L. So it's L on 2 plus x subtracts L. And then subtracts the overall distance, which is x, don't forget, multiplied by r8, the whole thing equals 0. Okay? So moving forward, we get move m to one side. Okay, so I'm gonna just race through this. Sorry about that. I'm gonna skip all the math here, guys. Sorry about that. Just px plus 3pl. I think that whole thing will be divided by 6. Okay, and remember, because this is an x, it's a function. Okay, it's always a function. Even if there is no x, it's going to be constant. Still a function. Well, so many mathematicians can argue it's not. So we want to find out. We know the starting point here. Where does it end? What's the ending point? Let's find out. X equals 2L is where it's going to end. But what is the value, the magnitude of the ending point? Again, sorry. Keep saying this, guys, but I'm just skipping the maths here just to make this video shorter for you all. 5pl on 6, that's the end point. So we go from here to there. It's a really small increase, small increment. 5pl on 6, okay? So we've gone up a bit. Alright, now, moving on, let's not waste any time.